Hi, in this video we're going to talk about section 13.4, the end of the chapter. So if the last video, or the last section really, was kind of, I don't know, confusing, I think this video is a nice cool down to that. And of course it's dealing with some of the same stuff, you know, to describe the spacecraft's flight. We want to know about how it moves through space, but this will feel a lot more like what you did in AB or Calc 1 than that last section. So let's start. We have a vector function r of t. This will be position. Gives the position of a particle, of a spacecraft, whatever, right? And it's literally a position vector. It's pointing from our origin right to where the position of that spacecraft is, or the particle is. Then velocity of that particle, the velocity of that spacecraft, is going to be a vector, v of t, and that will be the derivative, just like you would expect. The speed is the magnitude of velocity. Okay, so this is a scalar. It's not going to be a vector, and we don't really have a nice letter for speed, just like in Calc 1. We're just going to deal with that. And it'll be this familiar thing that we've probably gotten tired of, the magnitude of r prime, which is the arc length, or I guess it's the change in the arc length over time. And then we'd have acceleration. We'll call that a of t. This is definitely a vector. And you can think of that as the derivative of the vector v, the derivative of velocity, or the second derivative of the position vector. So all pretty typical fare that we remember. So like example, to shake off the dust here, given the position vector, our usual example of the twisted cubic, find the velocity, speed, and acceleration at t equals 1. Okay, as I've said in all my Calc 1 classes, Calc 2 classes, AP Calc classes, don't plug in 1 first, right? We take the derivatives, then we plug in. So you should all feel pretty confident getting me v, which is r prime by now, getting me a, which is r double prime. So go ahead and find me the velocity function and the acceleration function. 3, 2, 1. And again, I'm still calling these functions. That's not wrong terminology. They're just vector functions. Okay? So we found the velocity function. We found the acceleration function. Why don't I want to write speed? Well, we can write a speed function. We can find the speed of the particle as a function of time at any time. But it's really easiest to plug in the 1 first. And that's just 1, 2, 3. And the acceleration at time 1 is 0 to 6. And what about the speed at time 1? Then that would be the magnitude of 1 squared plus 2 squared plus 3 squared, or 14. The square root of 14. So notice again, the velocity is a vector, the speed is a scalar. It's the size of the velocity vector. Okay? Yeah, that's all there is to it. I'm not going to leave you there. We'll do one where we actually have to find the functions. So let's talk about a slightly different example. Give you another practice. I was going to say practical experience. Let's do root 2 in the I direction. Root t, sorry, the square root of t. T squared in the j direction, and e to the 2t in the k direction. And as always, I'm trying to do examples that aren't in the book. The book will have other examples if you wanted to go see, additional versions. Find me the velocity, find me the acceleration, and give me a speed function, speed of t. Okay. My velocity function should be r prime of t. So if you want to try it yourself, pause and come back. 3, 2, 1. So that would be 1 over 2 root t I hat plus 2t in the j hat direction plus 2 e to the 2t in the k hat direction. I'm just now realizing I probably want more space for my acceleration and my speed. So my acceleration function is the derivative of the velocity function. Just to show my notation off here. So you want to be careful with your signs and your powers here. 1/4 t to the 3 halves plus 2 in the j plus 4 e to the 2t in the k. So as ugly as those are, they're really going to be a lot nicer than the speed. So check that you have these two correct. And then when we find the speed, I'm even going to change colors for this. I'm going to find the size of that velocity vector as a function of time, meaning we're going to have to keep the t's in here. And it really is not a lot of fun. That's why, again, always plug in the value for t if you can. Here, not before you take the derivative, or else you'll always get 0. Here I go. Try it yourself. 3, 2, 1. I'm getting 1 over 4t plus 4t squared plus 4e to the 4t. All in the square root. And that's like just about as nice as that function is going to be. Obviously, you could simplify by finding a common denominator, but I'm not going to worry about that too much with you guys. I'd rather focus our attention on another example. So that was our derivative examples. It's enough to just go backwards a few steps. So how do we go backwards? So if I have someone tells me my acceleration function is e to the t in the I direction plus e to the negative t in the k direction. They tell me that my initial velocity is 1 unit in the I direction and 2 units in the j direction. So I'm not actually having any initial velocity in the k direction. And my initial position, 3i plus j plus 2k. So if they gave you this setup, can you go back and find the actual velocity function and find the actual position function? What would that involve? Well, my velocity function is going to be the antiderivative of the acceleration function with respect to time. And then I'll have to figure out the initial condition. So we're trying to integrate e of t in the I direction plus e to the negative t in the k direction, respect to time. Don't include the initial velocity yet. What do you get? I get e to the t in the I direction minus e to the negative t k hat plus c1 as a vector. Why is it c1? Because any calculus student knows if we're going from acceleration back to position, that's going to be 2 integrals. That's going to be 2 constant integration. They need to have different letters. The easiest way to do that is subscripts. Careful with your signs here. I may or may not have forgotten that in a previous take. So now we're going to plug in v of 0 is supposed to be I, then minus 1 in the k direction, plus c. I also know that v of 0 is also supposed to be I plus 2j. Which means that C1 is really 2j hat plus k hat. And if I'm trying to plug this into here, the easiest way to do that is to group the j with the j stuff up here. I'm not trying to point to the I. There is no j stuff here. And the k with the k stuff here. So try to write it out nicely. This is a review of what happened in 13.2. It should probably look like e to the t in the I direction, because nothing got added there, plus 2 in the j direction, because there was no j component before, and then plus 1 minus e to the negative t in the k direction. And now there's no plus c1 because we just plugged that in. We have a plus here because it just makes it easier. That negative sign's grouped there. It's really helpful if you group things like this when you have to integrate again. Like now. So r of t, the position function, would be the antiderivative of the velocity vector, which is, again, what we just wrote up there. Plus 2j hat, plus this group in the k hat direction with respect to time. So take your shot, write down what you would get when you integrate all three of those parts, keep track of the signs, keep track of the IJK components. 3, 2, 1. So I'm getting e to the t in the I direction, plus 2t in the j direction, plus quantity, careful with the parentheses there, t plus e to the negative t in the k direction, plus a different constant. So if you started off with just c, this needs to be like c1. Just call it C2. It really doesn't matter. So R of 0, if I plugged in 0 to all of this nonsense, I'm getting I hat plus 0 j hat, just to be clear, plus 1 k hat, again, plus C2, the adjustment factor. And if we plug things in correctly, that means 3i plus j plus 2k. So it's be I plus k plus c2. Which of course shows us that c2 is 2i plus j plus k. So if we put it all together, I'm just going to change color here. R of t is presto changeo, I shrunk it. So R of t, putting this all together, again, grouping the components. The I components need to go together. I got 2 plus e to the t in the I direction, plus 1 plus 2t in the j direction, plus 1 plus t plus e to the negative t in the k direction. And that's your final answer. So, is it work intensive? Yes, but it's just the same applications of your integration ideas from like, I don't know, not even chapter 1. It's from calculus 1. Calculus 1, that's what I meant. So, I hope this is a good review. In the next section, in the next chapter rather, we're going to get into much more interesting stuff. Actual multivariable functions. Functions that have 2 inputs and 1 output. These vector functions have had only 1 input, the t, and multiple outputs. And so now we're going to kind of reverse things. Having more inputs, 1 output, back to 1 output. Thanks for watching. Make sure you do the homework, and I'll see you in the next video. Bye.